You ever try to measure something from nature? I mean, it sounds simple enough, but it can get tricky and fast. Today, we're going to dive into the hidden math inside just a single leaf. And you know what? In the process, we're going to uncover the surprising geometric rule that connects this leaf to a slice of pizza and, yeah, even to bigger things. So take a look at this leaf. It's got this beautiful, really intricate shape, right? But if I asked you, hey, how big is it? Where would you even start? I mean, you could tell me how long it is, but that doesn't really capture the whole picture. What we're actually after is its area, the amount of space it covers. And that's the real problem. See, back in school, we all learned formulas for the area of a square or a circle, but nature, it doesn't play by those neat and tidy rules. There's just no formula for leaf. So what are we supposed to do when the rule book doesn't even have the answer? Well, to figure this out, we have to go way back to the beginning. We've got to ask a really basic question. What does area actually mean at its core before we even start thinking about any formulas? This is it. This is the real definition of area. It's not some complex equation. It's just a count. It's the total number of little unit squares, say square inches or square centimeters, that a shape completely covers. So the key thing here is we don't need a formula at all. We just need a way to count. And the solution is so simple, it's kind of beautiful. We just make our own unit squares by placing the leaf on some grid paper. And just like that, our abstract problem becomes a totally concrete counting exercise. The method itself is really straightforward. First, you count up every single square that is completely inside the leaf. Easy enough. Then you get to the tricky ones along the edge. For those, we just use a simple rule of thumb. If the leaf covers more than half the square, count it. If it's less than half, don't. And that's it. It's a surprisingly accurate way to get a good estimate. So, after all that, we've got our answer. By just counting up the squares, we can say with some confidence that this leaf has an area of about 46 square units. No complicated formulas, just simple counting. Okay, so we've totally figured out the space inside the leaf, but what about the distance around it? Let's switch gears and talk about the perimeter. Just like with area, the definition of perimeter is super direct. It's simply the length of the boundary. It's the total distance you'd have to travel if you were to walk along the entire edge of the shape. And we've got a couple of ways we can measure this. You could go really low-tech, just carefully lay a piece of string, or hey, even dental floss, right along the leaf's edge. Then you straighten it out and measure it. Or you could use a more high-tech tool called a planimeter. It's this cool wheeled instrument that you trace along the edge, and it literally calculates the distance for you. All right, now this is where it gets really, really cool. We know how to measure one leaf, but what happens when we compare a small leaf to a much bigger one? The math of how things scale up can be, well, pretty surprising. So let's set up a little scenario here. We have two leaves, same type, but the big one is exactly twice as long and twice as wide as the small one. It's a perfect 2x scale model. So here's the big question for you. If we double the length and the width, what do you think happens to the perimeter? And even more interesting, what happens to the area? Go on, take a guess. Okay, so the first part seems pretty logical, right? We doubled the length, doubled the width, and since the perimeter is just a measure of length, it makes perfect sense that it would also double. But the area, that's where the real surprise is. The area is 4 times bigger. Yep, not 2, but 4. And hey, if you guessed 2, you are in good company. This is one of those classic mathematical head-scratchers. And the proof is just so visual and satisfying. You don't need some complicated formula to get this. You can just see it. When you double the length and the width, you create exactly enough space to fit 4 of the original little leaves inside. It just clicks. So the whole key is understanding the difference in dimensions. Perimeter is a one-dimensional measurement. It's just length, a line. But area is two-dimensional. It has length and width. So when you scale a 2D shape, you're scaling it in 2 directions at once. And that effect gets multiplied. 2 times the length times 2 times the width gives you 4 times the area. They just scale differently. Now, this isn't just some fun little fact about leaves. This whole principle of scaling, it's absolutely everywhere. And getting a grip on it can actually help you make better decisions out there in the real world. Seriously, you see this all over the place. Let's say you're building a garden and you decide to double the length of the brick border. Well, you only need twice as many bricks. That's a 1D perimeter problem. But If a pizzeria offers a 16-inch pizza, it should probably cost about 4 times as much as an 8-inch one because it takes 4 times the dough, sauce, and cheese to cover that 2D area. And this isn't just a party trick. Educators really stress that understanding these kinds of proportions is a huge cornerstone of mathematical thinking. It's the kind of practical logic that really builds the foundation for more advanced stuff later on. So think about it. What started with a simple question about a leaf has actually unlocked this really powerful way of seeing the world. Knowing how 1D, 2D, and even 3D objects scale differently, it helps you see the hidden math that governs so much of what's all around us. We just saw that doubling a 2D shape makes its area 4 times bigger. So, what do you think happens in 3D? Let's say a small Rubik's Cube costs $5. What would be a fair price for one that's twice as long, twice as wide, and twice as tall? How much more material is that really? I'll let you do the math on that one.